Welcome back, learners. I welcome you all to my F5 IP DNS 302 complete study videos. So far, we have covered chapter 1. We have discussed on the basics of DNS with a simplified lab. We have discussed the TMOS architecture and base understanding and how the F5 DNS sits on top of TMOS on chapter 2. So in chapter 3, we are here in the chapter 3 where we will go through the design and architectural fundamentals. We will do a deep dive into the F5. We will go through F5 DNS. We will go through the core concepts and touch upon some of the advanced concepts. Chapter 4 would be mainly on the DNS lab. I've created a DNS lab for this course material learners. So we will discuss more on the lab and we will try to implement multiple scenarios. Then once we are covered with the lab in chapter 5, we'll go through the test and troubleshoot methods for the F5 DNS. And chapter 6, we will discuss on the exam review. This would be the bonus chapter for this study videos. All right, learners. So before we proceed further, if you like the content, please do like, share, and subscribe, and please provide me your valuable comments. All right, let's move ahead. So the table of content for this video is we'll go through the DNS overview and resolution process. We will talk about how the IP DNS is introduced. We will talk about how the IP DNS basics, what are its core concepts, what are its advanced concepts. We will talk about the load balancing methods, methodologies for the F5 IP DNS, and finally, we will run through some of the core advanced concepts of the IP DNS. All right, learners, let's move ahead. So let's try to understand how DNS works. We have gone through the basic of DNS in chapter 1 in depth. It's just a recap. For example, I have a local host that's trying to connect to local DNS server. Local DNS server will connect to root DNS, TLD, DNS servers, and finally the authoritative DNS server. This is how the logic flows. So for example, my local client machine tries to browse www.testf5.com. First, it checks its own cache, DNS cache, and it is not finding any record. It will try to query the LDNS server. LDNS configuration is as a part of a TCP/IP stack is configured on your client machine. It will query the local DNS server with testf5.com. The LDNS server is basically caching DNS server, plus it also acts as a recursive DNS server. The LDNS server will look on its own records, and if it's not finding the testf5.com, it will try to reach out to the root DNS server. Root DNS server is somewhat configured as a part of the hint zone file. In the local DNS, we have discussed the different zone files in chapter 1, but we will again cover the zone files from the F5 DNS perspective as well later in this video. So LDNS will try to give an iterative query to the local root DNS server. The root DNS says, reverts back mentioning that I don't know testf5.com, but I certainly know who is the authoritative name server for the .com domain, and it will give a referral to the referral as a name server of the TLD DNS server. Then LDNS will issue a iterative query to the TLD server. The TLD server will validate. It says, hey, I don't know the A record of testf5.com, but I certainly know who is the authoritative name server for testf5.com domain. It again gives back a referral, and the referral contains the name server record for the authoritative DNS server for the testf5.com. Finally, the LDNS will query the authoritative DNS server for testf5.com. The name server will do a lookup in its own table, and it finds a record. It replies back with the a record. DNS server, LDNS server will cache that a record in its memory, and then it replies back to the local host. So in this entire example, the LDNS is working on multiple iterations, right? And for the local host, the LDNS is a kind of authoritative name server. It's not aware of which authoritative name server it's hosting. It's like getting the A record from the local DNS server. So learners, this is how the TNS works at a very high level. We do have many design considerations later on. So let's move forward. So learners, before we introduce F5 IP DNS, let's try to understand the traditional DNS setup and the complications that are arised by this traditional DNS setup. So in a very traditional way, you have an array of DNS servers which are being load balanced, and you have a hidden master DNS server. And if this DNS architecture is facing internet, you have perimeter firewalls guarding your internal and external part. Basically, this would be a DMZ, and the DNS server would be housed in the data center. And when a client tries to connect to any of the web services hosted on the data center, the DNS query is load balanced by these legacy servers. 80% of the legacy servers are using Bind. Bind is the DNS program. So this looks good from a basic setup perspective, but what are the common problems we came across? First is the availability. DNS services are critical to availability, learners. We expect the DNS services to be functional 99.99%. All right. So in the legacy or the traditional setup, the servers are not ready to handle extra DNS queries. And if there is any DNS attack, for example, the DNS queries may spike up, and the legacy DNS servers are not ready to handle those many queries. Then what will happen? The legacy server may get overwhelmed, and the DNS services may be dropped, or it may get hung, right? So there is an issue with availability when the number of DNS queries raise. The number of DNS queries can be a genuine one, depending on the increasing demand, or it can be because of some DNS attacks. Now let's come to the second part, the security. We believe that the traditional DNS is less secure with the modern age. The cyber security attacks on the DNS is going complicated. We have numerous attacks like the DDoS attacks, like the man-in-the-middle attack, and even the traditional DNS server that's having the bind is very much susceptible and susceptible and vulnerable to the attacks. So it's considered as less secured. In terms of scalability, the servers are not that scalable, learners. So if someone tries to increase the capacity of a DNS server, it has to go through proper planning phase, and it has to go through some maintenance window. They have to increase the number of DNS server to cater to the DNS queries. So scalability is not that flexible in the traditional setup. The performance is quite slower in the traditional setup. We all know that the Bind is not an efficient DNS querying server. In a very traditional way, it kinds of resolves some 50,000 DNS queries per second. But the modern DNS infrastructure may require a server capable of handling more than 1 lakh DNS queries per second. So with all these 4 parameters at a high level, the traditional setup does look that it needs to be renovated with some new DNS architecture. Let's introduce F5 here, and let's see how F5 tries to address some of the concerns of the traditional DNS setup. So F5 DNS is acting as a one box solution for the multiple DNS concerns that we had. So we can have the DNS firewall in the F5 inbuilt. You can have the DDoS protection enabled. F5 does the protocol validation, authoritative DNS and caching resolver. It acts as a transparent caching server. It has high performance DNSSEC and DNSSEC validation, and finally, it is an intelligent GSLB. So many of the concerns that we discussed earlier are being addressed by the F5 IP DNS. It enhances the DNS performance. When I say enhances, F5 has the capability of handling 1 lakh plus DNS queries per second. That's a bit way ahead than the legacy bind server. And F5 enhances the availability. So F5 basically does a multi-data center DNS level load balancing. So if one data center is down, still the DNS will be routed dynamically to the other data center. The services would be available all the time. It's very easy to scale on demand with the F5 IP DNS. You can have multiple DNS servers load balanced or behind the F5. You can choose, how many servers can be enabled or disabled based on the pool members. At the same time, F5 DNS can itself act as a bind DNS server, can tries to resolve the wide IPs. We will discuss on the wide IP and the pool later in this section, learners. Then the most important thing is the DNS is secure with IPDNS. Okay, with F5 IPDNS, it has a very advanced DNS sec capability, and that handles your DNS DDoS. Plus, it gives some additional security to DNS as well with DNS Express. It has an enhanced caching and resolving capability to increase the scalability. And the last is the reporting and the analytics. So F5 IPDNS provides an enhanced logging facility that can be used for analytics, and that can be used for DNS traffic behavior as well. If you look how the IP DNS is built with the Big IP platform, we have a base Big IP platform that can be a hardware appliance or it can be a virtual edition. We have a TMOS as an operating system on both hardware. On the virtual edition, the TMOS is the base operating system. And we have the Big IP DNS module integrated with the TMOS architecture. So we have discussed about the TMOS architecture and F5 in chapter 2, learners. So just go through the chapter 1 and chapter 2. All right, learners. So let's try to move on to the basics and core concepts of Big IP DNS. So by now, we are clear that Big IP DNS is used in a multi-data center environment. It is mainly used when we want to do a GSLB load balancing between two different data centers. So as shown in this particular rough sketch, you see that GTMs are normally, they are working as a sync group. A sync group is a synonymous group wherein all the GTMs will share the same configuration objects, and the Big IP DNS, it load balances the VIPs. It can be LTM VIPs, or it can be VIPs from the generic host. Generic host are the non-Big IP products. They are the direct servers, and they're also having the DNS load balancing enabled by Big IP DNS. Plus, the LTMs are the Big IP products that have the VIPs behind them, and those VIPs are also load balanced. So learners, what we need to understand here is, if we know LTM has a VIPs load balance the real servers. Okay, here the LTMs, they load balance the real servers. DNS, they do a DNS load balancing of the virtual servers. So this is a basic difference when we talk about the Big IP DNS and the LTM. All right, learners. So let's try to understand the Big IP DNS communication with other Big IP devices. It's a very important section, learners. From the exam point of view and from your learning of the Big IP DNS, we need to understand how the DNS communicates with other Big IP devices. So there are three components that enable the Big IP communication with other Big IP devices. Just remember by heart. First is the scripts. There are three scripts: GTM underscore add, Big 3D install, Big IP add. There are two daemons, Big 3D daemon and GTMD daemon. and one communication protocol, that is the iQuery. So all these three components take care of the big IP communication. So let me open up a rough sketch on how the iQuery works. And before that, let's try to understand what these three scripts do. GTM add is used to add a new big IP DNS to an existing big IP DNS sync group. So this script is mainly used when you're adding a new big IP DNS and you already have an existing sync group. That sync group already have one or two acting big IP DNS servers. So the GTM add script will pull the configuration from one of the GTM that is a part of the existing sync group. You normally add this script on the new DNS server and you point to the IP address of the existing sync group DNS server. Big3D install, it's used to install the Big3D among other big IP devices. I will let you know what is Big3D later on. So for now, let's try to understand the Big3D is a data and metrics collection agent of any big IP device. It's very important to understand Big3D and GTMD learners. So from the version point of view, from the version point of view, all the all the DNS servers in a sync group need to have the same Big3D version. All right. Big IP underscore add. This is used when you add a new big IP device to on a big IP DNS box. So this command is added on a GTM or the big IP DNS, and it's used to add a big IP device that can be an LTM. Okay. Learners, we need to understand that big IP underscore add is mainly used to add LTM to big IP DNS, and GTM underscore add is mainly used to add a new big IP to the existing DNS sync group. We cannot add big IP DNS with this script, and we cannot add big IP LTM with this script. So be clear on this add scripts. So we discussed on the Big3D daemon, it's a data and metrics collection agent of any big IP device. GTMD, it's the core GTM process. It processes the GTM request, plus it also initiates the iQuery connection between different big IP devices. Last and most important is the iQuery protocol. It's basically an XML protocol that communicates between the other big IP devices. It communicates on TCP 4353. So to remember the port number, learners, iQuery is a very important exam point of view questions. You may get few questions based on iQuery, what port it uses, or what firewall rules are needed for the iQuery communications, or the port lockdown need to allow 4353. All right, learn. So let's try to understand a bit more from the sketch. So for example, I have a group of big IP devices. I have two DNS devices and two LTM devices. And here is where we need to understand the necessity of big IP DNS communication. The DNS communication is classified into two categories. One is to GTM to LTM, and the second is the GTM to GTM. Learners, sorry, I've written as GTM. GTM is nothing but your big IP DNS. So there are two communication necessities. One, the IP DNS tries to communicate to LTM, and the second, the IP DNS tries to communicate between the IP DNS in a sync group. So how this communicate initiates? GTMD daemon, as we discussed earlier, it tries to communicate the Big3D daemon of the local DNS server using iQuery protocol. It tries to establish a connection to the Big3D of the remote big IP devices using iQuery protocol. So GTMD will have a full mesh connections. One, it tries to connect to a local Big3D, and the other, it tries to connect to the remote Big3D, and it uses iQuery as a communication protocol. So I would like to clarify one thing about iQuery protocol, learners. Normally, people who know big IP DNS, they map the iQuery as a communication between big IP DNS and big IP LTM. That may be partially correct. That's not 100% correct. iQuery is in fact needed for the local big IP DNS GTMD to the local big IP, sorry, local big 3D communication as well. It can be an exam question. So the first thing that iQuery does is it tries to communicate, establish a connection locally between the GTMD and the big 3D. Then it tries to establish a connection with the remote big IP devices. I hope it's clear. All right, so let's move on to the next. All right, learners, so let's try to understand the configuration objects. Okay, this is very important, and it's also important from the exam perspective as well. Let's try to understand what is a listener. A listener is let me see if I have some diagram for the listener. Oh, okay, no issues. Okay, a listener is a specialized virtual server that passively checks for DNS packets on port 53. When a DNS query is sent to the IP address of the listener, the big IP either handles the request locally or forwards the request to the appropriate resource. Okay, so when you understand, learners, what is a listener? Listener is the heart of a DNS, big IP DNS. You cannot say you have a big IP DNS configured without configuring listener. Listener listens for any DNS queries. If you want to have your big IP box configured as a DNS, the very first thing you do is configure a listener. Okay, so you can configure multiple listeners. A big IP DNS is answerable to the wide IP. Wide IP is, I will talk about wide IP a bit later. It's a local bind configuration, or it's the or is the DNS configuration configured on the local bind. Then you can have a second listener for the LDNS. So if some user tries to target the LDNS and F5 is in the screening mode for the LDNS is trying to give the front end resolutions. So you can use that listener. So we will talk more on the deployment methods in our lab learners. So when we create lab, we will configure, we will configure and deploy big IP DNS in different deployment modes. So one of the mode is like the F5 DNS. It load balances a pool of LDNS servers. So basically what it's saying is you can configure a listener for that purpose. Wildcard listener, I have not seen wildcard listener more often as a configuration, but it can be an exam point of view, learners. So let's try to understand what is a wildcard listener. It's a listener that is assigned a destination 0.0.0, that means any, and a DNS query port 53. So if you want the big IP DNS to respond to all DNS query coming into your network, regardless of the destination IP address, you can use the wildcard listener. So it can be a very tricky exam question. All right, so let's talk about the wide IP. Okay, I have a sketch as well for the wide IP. So after we configure listener, the wide IP is another important configuration object, learners. So wide IP is the F5 DNS FQDN to one or more virtual servers. Wide IP configuration decides which virtual server or pool is eligible to respond to the DNS query. So we can see here, you have a big IP DNS, you have two data centers. A pool 1 is configured in data center 1, pool 2 is configured in data center 2. Pool 1 essentially load balances the VIPs, VIP 1 and VIP 2 in data center 1. Pool 2 essentially load balances two VIPs in data center 2, VIP 1 and VIP 2. And these two pools are load balanced by the wide IP FQDN. So when a user tries to hit the wide IP is configured on the big IP DNS, and it tries to load balance between these two pools, and the best available VIP IP is returned out of this 4 IP address. So wide IP is your FQDN, and that is resolved to the VIP IP at a very high level. So just remember that, learners. We also need to remember the characters in the wide IP, like the names and aliases, the question marks, the asterisk, and we need to understand that wide IP, you also get some sort of persistence. We can connect and persist at a wide IP level to make sure that the connections from a particular source is directed to a particular WIP or to a particular data center. Wide IP as a last resort pool. So this is where this may be an exam point of view question as well, learners. So the F5 DNS uses the resources included in the last resort pool only if the no other resources are available to handle the DNS queries for the wide IP. So you have, say for example, for the wide IP, you have configured pool A, pool B, and then you configure the last resort pool. So in an ideal situation, the wide IP will try to load balance between pool A and pool B. But if there is any disaster and both the pool A and pool B are become unavailable, then the administrator can configure a last resort pool that will be used to serve the wide IP DNS query. All right, learners. So we talked about wide IP persistence, and it's very important to understand how big IP DNS persistence works. It may be an exam question as well. So we know that the persistence is configured at the F5 wide IP, DNS wide IP. LDNS makes a request for wide IP that has persistence enabled. The DNS makes a load balancing decision and provides an available resource web and generates a persistence record. Now, within a synchronization group, this DNS will also try to forward the persistence record to the DNS peers because this is very much needed for config sync of the big IP DNS. Then the subsequent DNS queries from the same LDNS is routed as per the persistence until the persistence TTL value. So it's basically you are persisting connections from an LDNS to a particular web or particular data center. Now, what are there in the persistence settings? You have a TTL that specifies seconds, the length of time persistence entry is valid. The default is 3600, it's 1 hour. Then you mentioned the persist CIDR for the IPv4, the default is 32. You mentioned the persist CIDR for IPv6, that's default is 128. All right, learners. So far we have learned about the listeners, we have learned about the wide IPs, we have learned about the wide IP persistence. Now let's learn core components, configuration components of an IP DNS. I call these three as a core components because if you want to function your big IP DNS, you need to have a data center defined. Data center are like grouping of services and applications. They are typically located in the same physical location. You can also do a logical grouping. Not necessarily the devices or the need to be in the same physical location, but you can also do a logical grouping, and you can call them in a particular data center, say data center A, data center B, or data center C. So the data center configuration, it allows the big IP DNS to understand the location of your services logically for the purpose of high availability and resiliency. Now, once you configure data center, you configure servers. A server is a physical system on the network. Servers may have virtual servers that are the destination of the wide IPs. We have already learned that the wide IP load balances the WIPs. So the virtual server, a server may be configured within a data center, and big IP DNS supports the following servers. Okay. The first can be the big IP systems, any member of the big IP product line. It can be big IP LTM essentially. Third party load balancers, a server can be from the Cisco, or it can be a Citrix NetScaler or any other third party vendor. A server can also be a third party host server. It can be a direct Linux machine or Windows server. You want to directly load balance them, and these are mostly called as the generic hosts. We discussed about generic hosts in the core concepts, learners. So Big IP DNS, it load balances the virtual servers that can be a part of Big IP systems. It load balances virtual servers that can be a part of third-party load balancing. It load balances the virtual servers that are configured from a part of the host server or called the generic hosts. So once we configure data center, once we configure servers, now we configure pool and pool members. So pool is a collection of virtual servers and pool member is a virtual server. So here, this is what I was talking about. For each and every data center, you have a pool. Pool is a collection of virtual servers. There is a separate load balancing happens under the pool, and there is a separate load balancing happens at the wide IP. So I will talk about the tiered load balancing of the big IP DNS a bit later. What I meant by tiered is you have two levels of load balancing, one at the pool level and second at the wide IP level. All right, learners. So let's try to understand prober pool. Okay, let's not get it confused with the pool configuration that we discussed earlier. That pool was a member of, that pool has a configuration objects as virtual servers. And here, prober pool is something that is a collection of one or more big IP systems in order. In F5 sync group, we can have multiple prober pools, and F5 DNS can be a member of multiple prober pools. So learners, it's very important to understand prober pool from the exam perspective, and if you're trying to set up F5 DNS in any of the enterprise architecture. So what prober pool does is the members of prober pool perform monitor probes to servers to gather data about the health and performance of the resources on the servers. The big IP DNS makes a load balancing decision based on the gathered data. If all the members of a prober pool are marked down or if a server has no prober pool assigned, the DNS reverts to the default intelligent probing algorithm to gather data about the resource server. So what it essentially says is the prober pool is normally configured to localize the monitoring of the servers or the data centers. So ideally what happens if we create a larger big IP synchronization group consisting of multiple data centers, multiple big IP DNS devices, multiple big IP LTM devices. If we don't configure prober pools, big IP DNS uses its own algorithm to set up monitoring probes or to do a monitoring setup to the backend or to the virtual servers, right? So based on that data, Big IP, what Big IP DNS do? The wide IP load balancing is purely based on the metrics gathered for the availability of the VIPs or the generic hosts. So how this metrics is gathered? It can be done if the prober pool is not configured. That is done by the algorithm, native algorithm of the Big IP DNS. But if you want to localize the monitoring, say for example, I have a data center one and I want all the server objects of data center 1 to be monitored by my F5 DNS1. I have a data center 2 and I want all the server objects to be monitored by F5 DNS3. I have a data center 3. I want all the F5 server objects to be monitored by F5 DNS5. So this is where we configured prober pool. We order the prober pool. For example, I'm ordering DNS1 with order number 1 and DNS2 with order 2. The first priority would be DNS1, so the DNS1 will do the monitoring that is in the interest of the localization of monitoring. If DNS1 will check the server objects, it will check if the VIPs are up and down, it will gather that report, provide to the GTMD, GTMD takes load balancing method based on that report, it trusts the localized monitoring, right? And based on that, the load balancing happens. If a DNS1 fails, is marked down, then then the DNS2 does the probing part. It does the health checks for the virtual servers and it gathers data and provides the GTMD process of the F5 DNS. So what we need to understand, learners, the main purpose of prober pool is to trust the localization of the monitoring of servers. If you don't configure prober pool, then F5 DNS will dynamically run its own algorithm, and it will dynamically allocate any of the F5 device to monitor the server objects. That may or may not be an optimal solution. So as a best practice, we do configure prober pools. All right, learners. So let's try to now understand a very important concept of F5 DNS setup. That's called the configuration synchronization. So we already learned the necessity of F5 big IP DNS communication. Where do we need? We may need communication between the F5 DNS to F5 DNS, and we may need communication between F5 DNS to other big IP system. So a sync group is essentially a group of F5 DNS devices that share the same configuration and metrics. Config synchronization occurs in the following manner. So for example, a change is made in this. So for example, we have 3 big IP DNS devices in the sync group, and a change is made in the big IP DNS1. So that change is communicated by the MCPD. MCPD is your code process that tracks all the changes, and that relays that change to the GTMD process. The GTMD process, what it does is it takes a note of that change, it updates the GTM configuration file. At the same time, it increments the commit ID. So in effective, what happens, and it also relays that information to Big3D. Big3D is our monitoring agent, right, guys? We discussed about Big3D a few minutes before. So Big3D essentially it validates it does a periodic check to all other big IP devices, DNS devices, and sync group. It checks if the commit IDs are equal or not. So whenever there is a change happened in the GTMD configures or make changes to the GTM configuration file, it increments the commit ID value, and it informs the Big3D about the incrementing commit ID. So the Big3D immediately relays the commit ID to the other big IP DNS devices using the iQuery protocol, that's TCP 4353. Then the other devices, they compare the commit ID that's configured on their GTMD process. They validate, they say, okay, my commit ID is less, and I say that DNS1 is having a higher commit ID, so it will request for the configuration change. Similarly, DNS3 will check its commit ID, and it will compare. It will say, okay, my commit ID is less than the commit ID of the big IP DNS1. It will again do a request for the configuration change to the DNS1. DNS1 replies back to both of these DNS boxes, and it provides the configuration change in a record. Now, in return, these DNS boxes, they update the configuration in their GTM configuration file, and at the same time, they also increment their commit ID to the next value. Now, the Big3D again does one more comparison of the commit ID as a part of periodic monitoring. It checks that the commit IDs are now in sync and no further configuration sync is needed. So this is how, at a high level, the synchronization works. And when a configuration synchronization is in progress, the process must either complete or time out before another config sync can occur. So it's very important to understand this, learners. So if there is an existing synchronization progress, it cannot make a new configuration synchronization. That will not be effective. Two of the most important things, the NTP, you should be running the NTP on all of the DNS boxes, and the Big3D versions should be same, should be matching across all of the members in a config sync. All right, so let's review the requirements of a config sync group. The DNS synchronization group members, they must run the same software version. The synchronization parameters must be properly defined for all the members. You should have the same sync parameters defined when you configure the sync. NTP must be configured. It's very important. It's not optional. It's mandatory. Port lockdown must be set properly for all relevant self IP address. You need to open the TCP port 4353 for allowing the iQuery. Okay, one important thing to note here, learners, that the management IP address are not compatible with iQuery. You cannot use them. You cannot use the management IP to run the iQuery. You always need to use the self IP address. It can be an exam point of view why the iQuery is not working. So you need to make sure that the iQuery is targeting the self IP and not the management IP address. You need to have the compatible Big3D versions installed on all synchronization group members. We discussed this multiple times, the importance of a Big3D. Big3 is a monitoring agent, and if there is any version mismatch, then it will not work as expected. And if the Big3D communication fails, your sync group communication will fail, and the configuration sync will not happen. And last but not the least, you need to have a valid device certificate to be installed. So learners, whenever we try to add big IP GTM to a sync group, the very first thing it will do, it will try to exchange the device certificates. Device certificate exchange is needed to establish a trust between the GTM or the DNS peers. So if you don't have a valid certificate installed, the trust is broken and the sync will not happen. So it's very important that you remember these 5 to 6 requirements. You may get a lot of questions. Uh, Say, for example, sync group is broken. You may be asked to find out the reason. So just remember these 6 points and you should be able to answer it properly. All right, learners. So let's try to understand what things are synchronized with the config sync by default and what are not. So you will have the wide IP that is synchronized by default. So whenever you say the synchronization is enabled, you will have the wide IP address synchronized. You will have the data center synchronized. You will have the servers synchronized. You will have the virtual servers synchronized. The links are synchronized. Topology records, distributor application, GSLB global settings synchronized. GSLB monitors synchronized. DNSSEC zones and keys are synchronized. Name configuration and DNS zone files. These are the two files that are not synchronized by default, learners. You need to enable them. Whenever you're performing a sync, you need to enable them. Okay, let me just try to see if I have a lab device. I can just show you a real quick what I'm talking about. Okay, let me see if okay, let me log on. So learner, this is one of my lab box. So while working with the lab, I will be discussing more on this lab section. For now, let's try to understand what I'm talking about, the synchronization. So you go to settings, delivery, sorry, GSLB in general, okay? So you can see this is where this is all the synchronization parameters that I was talking about. And if you scroll down, okay, so you can see what all are allowed and what are not allowed here. And you can see the load balancing methods. We will discuss about in-depth, learners, when we configure our labs. We will discuss on this. Okay, we said that, what did we say? Zone files and name configuration. Okay, there you go. So the synchronized zone files, it's unchecked by default. So all these things are checked by default. So if you want to synchronize the zone files, you need to click here. And forward status, it's also disabled. You just need to enable it if you have a forward status requirements. So we'll discuss in-depth, learners, on these parameters. No need to worry for now. For now, let's try to remember what things are synchronized and what things are not synchronized by default. This can be an exam question as well. All right, learners. So let's come to the most interesting part, F5 IP DNS load balancing. We have indirectly discussed about the load balancing methods earlier. So this is an extract from the F5 DNS portal. So it's very important, learners, that we understand all these load balancing methods. We understand where it's needed. There may be multiple questions based on this load balancing methods. So just go through this. And what I would be more interested is what load balancing methods are applied at the wide IP level. So if you remember, learners, right? If you remember, we discussed on a tiered load balancing method. So F5 DNS is basically offers a tier load balancing method. A first load balancing happens at the pool level. You can have a round robin, least connection, and other load balancing methodologies that has been described here at the pool level. And the second load balancing happens at the wide IP level. The wide IP will select at the pool A or pool B based on the load balancing method selected. At the wide IP, you have only four load balancing methods, learners. Just remember, these are very distinct parameters. The global, you can configure global availability, you can configure ratio, topology, and round robin. Global availability, ratio, topology, and round robin, only these four load balancing methods are applicable at the wide IP level. All right, you cannot configure it into DNS, you cannot configure none or drop packet at a wide IP level as a load balancing method. All right, so okay, so once we configure the load balancing, let's try to understand how the resource availability is calculated. It's very important, learners, we understand how the resource availability is considered on the F5 IP DNS. So there are three methods that FIP DNS uses. One is the dependency on another resource, second is the limit settings, and third, a set of the values written by the monitor. So third one is quite familiar. You have a monitor that checks the resources on port 80, 443, or whatever ports. And if it is monitored, yes, then it will be considered as available. A dependency on another resource is, we talk about virtual server dependency, right? So in BigIP DNS, you can configure a virtual server to be available based on the availability of another virtual server. So let's try to understand what it's trying to say. So you have two virtual servers, say virtual server A and virtual server B. The application architecture has a requirement that virtual server A should be marked available only if the virtual server B is available. The reason for that is both are interdependable virtual servers and services. So for that reason, you can configure this virtual server dependency. Learners, you need to understand this. It can be an exam question point of view. So the BigIP DNS uses this virtual server dependency as one of the methods to determine the resource availability. In limit settings, we set the thresholds to make sure that if particular WIP is available, if until its threshold is 80%, something like that, utilization. And the third is the monitor settings, like that will make whether the virtual server is up, down, based on the health monitors configured. Now, at the pool level, learners, we know that there is another load balancing happening at the pool level, but you have the three configuration parameters you need to decide before you set the pool level load balancing. You have a preferred load balancing method, you have an alternate load balancing method, and you have a fallback load balancing method. The first load balancing method is used to return the IP address of the virtual server in a response to a DNS name resolution. The preferred method, it can be either a static or it can be a dynamic. Now, if the preferred load balancing fails, it is likely that the BigIP DNS was unable to acquire proper metrics to perform load balancing. The alternate method can only be static. So once the prefer fails, it falls back to the alternate. Alternate cannot be a dynamic load balancing method, learners. You cannot assign a dynamic load balancing method to the alternate method, and it can be an exam point of view as well. They may ask you a question, what load balancing method and is it related to the alternate load balancing method. You just have to make sure that you're selecting only the static methods, not the dynamic ones. The reason for that is the alternate thinks that the BigIP DNS was unable to acquire proper metrics to perform the load balancing in the preferred load balancing method. Now, if the alternate load balancing fails, the preferred fails, the BigIP DNS falls back to the fallback method. To ensure the BigIP GTM returns a request to request, the fallback method ignores the availability status of a resource. So the fallback, it essentially it ignores the availability. It says that I don't care what the availability status of resource is, but it still returns the response. The fallback method can be either static or dynamic. Now, if all of these three methods fail, if all of these three configured load balancing methods fail to provide a valid response, either the request fails or BigIP DNS uses the local bind to resolve the request. So it's very important we understand these methods and we understand the last line when all of the three methods fail. All right, learners, it's very important to understand the topology load balancing. I have seen multiple questions being asked on the topology load balancing. Topology is basically a proximity load balancing method, and it redirects the client to the data center housing the resource that responds to the request. When topology load balancing is enabled, the BigIP system uses topology records. So there are two components that we configure for the topology load balancing. One is a topology record. A topology record is a set of characteristics that maps the origin of the DNS name to the destination. So what topology record does is it maps a particular DNS, it maps the origin of a request based on the DNS, LDNS, and accordingly it redirects that to a pool, right? So a request from a source statement specifies that the origin LDNS of a request, a destination statement that specifies the pool of pool members. So let me see if I can show you in the configuration. If I go to topology, all right, this is what I was talking about, topology record. So you need to select the request source and you can say that the client, if the region is client, then the pool is say ABC, and you can give the weight as well. A weight that the BigIP system assigns to a pool member during the load balancing process. So in TMSH, the weight parameter is called the score. So it's just a configuration difference when you do configure by the GUI or the TMSH. So there are some user-defined regions as well. A region is a customized collection of topologies, as you can see. Right, so topology has records and regions. Okay, so first you define regions. If in a region you define what IP subnets you have in that particular regions. Okay, don't worry, learners. I have a very detailed lab for the topology records that will clarify your doubts. So basically, you first define regions and then you create records based on the defined regions. So okay, so it's just you can use the custom regions as the request source or destination of a topology record. All right, learners. So till now we have covered some of the core concepts, the basic concepts, the F5 DNS. We have covered the load balancing methodologies of the F5 DNS. We have covered the uh, configuration objects of the F5 IP DNS. Now let's move on to the advanced concepts, and the first is the zone runner. So zone runner is a utility that is used to create and manage DNS zone files and configure the bind instance. So a normal bind a DNS bind server, you do a change at the bind level, but at the F5 big IP DNS, it provides you an utility to make the changes. If you want to import and transfer the zone files, you use zone runner. If you want to manage zone resource records, you use it with the zone runner. If you want to manage views, you use the zone runner. If you want to manage a local name server, if you want to transfer the zone files to a name server, if you want to import only primary zone name files, so you use the zone runner. Learners, we have discussed in depth on the zones and the zone data files in chapter 1. So I would request you to review chapter 1 thoroughly before we understand and move ahead with the zone runner. So the next part to understand is the named conf. Named conf is the bind configuration file. For the F5 DNS, it includes the DNS views, access control list, definitions, zones. Please use zone runner utility to edit named conf. Do not use directly make changes to the named conf by going to the SSH. Always use and trust the zone runner utility. So master DNS zone. A master DNS zone is an authoritative for its zone data. Below are the steps to create a master DNS zone. You go to DNS zones, zone runner, zone list, create. You see the screen opens. Select external from the view list. External is view as the default. In the zone menu, you place the dot character. Select the master from the zone type. We will discuss about the zone types a bit later. Type in the zone file name in the record section. Type the values of the start of authority and the names of our records and click finish. So if we just look how it looks at the GUI, zones using zone runner. If you're creating a zone, you have to mention the view name, you have to type in the zone name, what the zone type is. We have so many zone types. It can be a master, slave, stub, hint, forward. Configuration, this is a named file configuration. This is the start of authority record, the name server record. So you need to fill all these details when you create a zone using the zone runner. All right, learners. So we learned about the master zone file. So what is a hint zone? Hint zone points toward the root name servers. When the local name server starts, the name server queries the root servers in the hint zone for the most current list of the root servers. Allowing zones files transfer. Okay. So learners, it's very important. It can be an exam question as well. Zone transfer is not allowed by default. Okay. So this is for the security reason because the zone transfer is not regulated that securely like the other transfers, right? So for that reason, we put a check that the zone transfer is not allowed by default. You need to click on zones, zone runner, name conf, and in the options field, you need to modify the allowed transfer to include the IP address of the F5 DNS or the name server. So for example, the allowed transfer should look like this. If I'm allowing 192.168.10.105 for zone transfer, I need to explicitly mention that in the options field in the named configuration file. And there is an access list as well. You need to update the access list, allowing that particular host for the zone transfer. We talked about DNS views. DNS view is like creating multiple name server configuration on the same server. It's like creating a multiple contexts of DNS within the same F5 DNS. You can have like internal, external views or internal DNS and external DNS configured using DNS views. So the type of zone files, learners, we already discussed about the primary zone, the secondary, they are the slave name server. Zone files for the secondary zone are copies of the primary zone files. So you make changes on the zone files on the primary. You allow zone transfer, and secondary just copies that primary zone files. And the intervals is specified in the SOA record. Secondary zones query the primary zone to check for the secondary and obtain the updated zone data. A secondary zone responds authoritatively for the zone provided that the zone data is valid. Then the stub zones are similar to secondary zones, except that the stub zones contain only the NS record for the zone. Note that stub zones are a specific feature of the bind stub implementation. So if there is a requirement of bind stub implementation, you create stub zones. Forwarding zones contains only information to forward DNS queries to another name server on a per domain basis. The hint zones we discussed, it specifies an initial set of root name servers for the zone. Whenever the local name server starts, it queries for the root name server. All right, learners. So we are now coming to one of the most interesting advanced concept that's called the DNS Express. DNS Express is a high-speed authoritative secondary DNS server. Big IP DNS answers DNS queries for a DNS zone and responds to zone transfer requests. So DNS Express is needed when you want to hide your authoritative name server behind F5, and F5 acts as a high-speed authoritative secondary DNS or the slave DNS server. Okay, so and the zones are loaded from the authoritative DNS server to the DNS Express. Okay, so DNS Express, it provides an additional security to your name server, plus all the zone transfer is secured with the transfer signatures. We'll talk about TSIG a bit later. So what essentially happens is when the F5 DNS, when the DNS Express is enabled, and you create a zone you're creating a DNS Express is exact replica of that zone name. The zone name is exact replica of the zone name on the authoritative DNS server. So once you create the zone on the IP DNS, it initiates a zone transfer request. All right, so the moment you start creating a zone, let me just show in my lab box. Okay, learners. So we need to understand there are two ways to create zones. Okay, the first is via zone runner. Zone runner is used to create zone on your local bind existing on the DNS. And the zones where we configure for the DNS Express is this part, learners. It's not under zone runner, it's under zones. So when you create a zone using the DNS Express, for the DNS Express, you create the zone name. The zone name is exact replica of the zone name. You have it on the name server. Here you need to configure server. I will explain a bit what configuration is needed, what do I mean by server here. And you configure the zone transfer clients used for the zone transfer and the TSIG, what I talked, right? The transaction signature. So you need to configure this as a part, these parameters as a part of the DNS Express zones. So the moment you create zone, it initiates a zone transfer request. DNS Express from the to the authoritative DNS server. The authoritative DNS server responds with the zone transfer, and DNS Express loads the zone. So let's try to understand a bit deeper on zone transfer. There are two scenarios, learners. Okay, we already discussed what the DNS Express is used. It can be used to answer the DNS queries for a DNS zone, or it can be used to respond to zone transfer requests. So responding to client DNS queries. Okay, so let's talk from right to left. Okay, you have a site, say for example, ABC site is updated on the name server. The authoritative name server will send a zone update notify message to DNS Express. So we already considered that the authoritative DNS server has the F5 DNS Express IPs in the allowed list for notify and zone transfer. So the authoritative, it sends an notify update. The DNS Express, once it gets the notify update, it sends a zone transfer request, and the authoritative name server completes the zone transfer. So the DNS Express is now updated on the zone, so they are in sync. Now when the LDNS queries for the same domain, say ABC, the DNS Express will reply back with the A record for that zone, and it will act as an authoritative name server for that zone. This is one scenario. Then the second scenario is wherein the DNS Express sits in between two authoritative name servers, the master and the client. So if we remove this DNS Express, learners, why would we need a DNS Express in between the master and the client? If we in chapter one, we discussed in depth on the zone transfer between the master and the client, or the master and the slave. Okay, and that was an X5 DNS was not included there. So if you remove the F5 DNS, they can still have the zone transfer, but those zone transfers are not that fast, quick, or and also those zone transfers are not secure. So as we said earlier, zone transfer itself is not a secure transfer method. It requires some sort of device that secures the communication, and here is where the F5 DNS Express comes into picture. So whenever there is an update in the zone, the server, DNS authoritative DNS server, sends update notification. DNS Express sends the transfer request, and the zone transfer is completed by the authoritative name server or the master. So once the zone transfer is completed, DNS Express sends update notification to the client DNS server. The client DNS server sends a zone transfer request, and the F5 DNS completes the zone transfer. So we need to understand these two scenarios, learners, from the DNS Express and what is the necessity of it. And I think that should be clearing a concept of the DNS Express. So the configuration I steps that's needed. First, you configure a name server. A name server is very much essential. It can be authoritative DNS server that hosts a DNS zone, or it can be a VIP that's load balancing a pool of DNS servers. Then you configure DNS server to send notify on the name.conf file we discussed a bit earlier. Then we create a DNS zone. We discussed how we create a zone. It is not a zone runner zone, but it's a different zone you want to create in the DNS Express engine to answer the DNS queries. The zone must be exactly the same on both big IP system and the authoritative DNS server. And to secure the zone transfer, we configure the transaction signatures, or the TSIG. TSIG is a networking protocol that provides a secure methodology for communicating between the primary to secondary DNS server using a shared key, and is added to all DNS packets exchanged between the servers. It ensures that the DNS packets originate from the authorized name server and have not been altered and en route. So the authenticity is guaranteed between the zone transfer. All right, learners. So we now arrive to a concluding concept or topic for this video, and that's called the DNSSEC. DNSSEC is an industry standard protocol that runs with an extension of the DNS. It essentially secures your DNS queries. It secures your DNS zone transfers. It guarantees the authenticity of the DNS responses, including the zone transfer. It returns the denial of existence responses. So DNSSEC is a secure feature that's added with F5 DNS learners. So configuration wise, it's twofold. At the minimum, you first configure the DNSSEC keys. DNSSEC keys comes in two flavors: the zone signing key and the key signing key. You configure DNSSEC key, then you create a DNSSEC zones. Let me open my lab box. So here, go to delivery, I go to keys, I go to DNSSEC key. So I can just create a DNSSEC key. I can say whether it's a zone signing key or whether it's a key signing key. It comes in only two flavors, and I fill in the parameters. Okay. So once I create the DNSSEC keys, I need to declare a particular zone. For example, I've declared my testf5.com as a DNS secured zone. So similarly, you can create and you can configure what JED-SK zone signing key and what KSK the zone would need it for its security, and you mark the state as enabled. So zone signing key is essentially a key that's used to sign all records of a DNS resource record set. A DNS resource record set is a set of common configuration of the zone objects, right? The EA records or the name server records. You segregate each records in a set of records. those records are classified as DNSSEC resource records. Key signing key is only used to sign the DNSSEC key. Okay. So the DNS security is enhanced with the rotation policy. So there are two ways you can use the DNSSEC keys. Either you can manually update the keys after every year, or you can after or a particular period of time, or you can use the rotation policy, right? So we need to understand what is the rotation policy. A rotation policy is basically you have the policy wherein you will have an overlapping time. Say for example, my key expiration period is 37 days, the rollover period is 30 days, and in the background it creates a generation 0, generation 1, and generation 2 keys. So during this overlapping period, it does a key rollover and the keys are modified or changed. Okay. So TTL of 6 days is valid. So for example, the moment the expiry date is 37, after 30 days, and the beginning of the overlapping, it generates one more key. And once the key is expired, you have the new key ready to be enabled for the next period. Yeah. So we normally recommend rotation policy to be enabled for enhancing DNS security. All right, learners, with this, I conclude today's session, today's video of F5 DNS design and architecture. I hope it was useful to us. It may be a lot of theory, but learners, be assured in the next session, it will be pure lab. Whatever scenarios we have discussed so far, I will cover those scenarios one by one. And with the lab, a lot of things will be clarified. All right, with that, thank you all for listening, and we'll see you soon.